Welcome. This is HTTP, the web's universal language. Explain the way a senior engineer actually thinks about it. Over the next 25 slides, we'll trace the protocol from its 1991 origins at CERN all the way to QUIC, covering the request lifecycle, status codes, headers, the TLS handshake, and the performance and security trade-offs that shape every system you build. 5 sections, about 30 minutes, and by the end, you'll have real fluency, not just familiarity. So before we go anywhere, let's ask the obvious question. Why does HTTP even exist? It solves 4 problems that nearly killed the early web. Interoperability. Instead of every app inventing its own protocol, we got one shared language. Statelessness. Servers stop tracking every connection, so each request stands on its own. Scalability. That independence is exactly what lets modern infrastructure handle billions of requests a second. And simplicity. It's plain text, debuggable with curl or even telnet. That combination is what turned the web into a global platform. With those 4 problems in mind, it's worth seeing how HTTP itself evolved to keep solving them. In 1991, it was a single line, get, a URL, that's it. By 96, we had headers and status codes, then persistent connections in 1.1, which ruled the web for 16 years. HTTP2 brought binary framing and multiplexing in 2014, and HTTP3 moved the whole thing onto UDP via QUIC for sub-RTT handshakes. The key insight: all 4 versions are still live in production. Your browser negotiates the best one each server supports, which is why version awareness is non-negotiable for senior engineers. Now strip away the version drama and HTTP collapses into something almost embarrassingly simple. 2 messages. The client sends a request. The server sends a response, and both share the exact same skeleton. A start line, some headers, a blank line, and an optional body. On the request side, that start line is method, URL, version. On the response, it's version, status, resin. Everything else, auth, content negotiation, catching, is just headers riding along. Internalize this shape and genuinely, 80% of web debugging becomes pattern matching. So with that 2-message shape in mind, let's zoom out and watch where it actually fits in the bigger picture. From the moment you hit enter on a URL to the moment pixels appear, 8 distinct things happen. A DNS lookup, a TCP handshake, a TLS handshake, the HTTP request, server processing, the response, browser rendering, and then a cascade of additional requests for images, fonts, and scripts. Steps 4 through 6 plus 8. That's pure HTTP territory, and that's where we're spending the rest of this deep dive. Inside that HTTP territory, the very first thing the request carries is a verb, and there are exactly 7 that matter. Get, post, put, patch, and delete handle your daily CRUD work, while head and options quietly power things like cache validation and course preflight. The column to watch is idempotent. Get, put, delete, head, and options can all be safely retried, but post and patch cannot. Fire them twice, and you might create 2 users or double apply a change. That single distinction is what makes retry logic safe or dangerous in production. Once the verb is out the door, the response comes back wearing a 3-digit badge, and the first digit is all you really need to triage. 1 exec is informational, and you'll rarely see it. 2 exec means the server did what you asked. 3 exec says, go look somewhere else. 4 is you breaking the contract, and 5 exec is the server falling over. When you're scanning logs at 2 a.m., sort by class first. 5 QUICs, drop everything. 4, check your code. 2, move on. Now, narrowing from classes to specifics, there are over 40 standard status codes, but in production, you'll really only meet 16. The greens are your happy path. 200 for a clean success, 201 when a post creates something, 204 when there's nothing to send back. The blues redirect, 301 permanently, 302 temporarily, 304 telling the browser its cache is still good. The oranges are client mistakes, 400 malformed, 401 missing credentials, 403 authenticated but blocked, 404 nothing there, 409 a state conflict, 429 you're hitting too hard. And the reds are server side, 500 your bug, 502 and 504 an upstream problem, 503 capacity or maintenance. Learn these 16 and you can read almost any log fluently. Status codes tell you what happened. Headers tell you everything else. Think of them as the metadata layer wrapped around every request and response. Caching rules, content type, auth tokens, security policies, language preferences, all of it. There are over 100 standard headers, but they slot neatly into 6 categories. General ones that apply both directions, request-only headers the client sends, response-only headers the server returns, entity headers describing the body, security headers defending the page, and caching headers controlling freshness. Master these 6 buckets and the other 90+ stop feeling intimidating. Let's start with the request side. The 8 headers your client sends on virtually every call. Host tells the server which domain you want, since one IP can serve many sites. The user agent identifies what's making the call, accept encoding, negotiate format and compression, and authorization carries your credentials, usually a bearer token. Cookie ships session state back. Referrer reveals where the click came from, and content type declares your body format on posts and puts. Browsers handle these silently. When you're writing API clients or debugging with curl, you set them yourself. Now flip the conversation around. Here are the 8 headers the server sends back. Content type and content length describe the body so the client knows how to parse it. Cache control and e-tag are your caching workhorses. Tune them well and you offload most of your traffic to browsers and CDNs. Set cookie plant session, state, location drives, redirects, and www authenticate pairs with a 401 to tell the client which auth scheme to use. Server identifies the software in Topuri, and in production, you usually want that one disabled. Speaking of set cookie, that one deserves its own slide because HTTP itself remembers nothing between requests. Cookies are the duct tape that gives us sessions, logins, preferences. The server says, remember this, the browser stores it and echoes it back on every subsequent request. The attributes are where the real engineering lives. Domain and path control scope. Max age controls lifespan, and the security trio matters most. Secure keeps it on HTTPS. HTTP only hides it from JavaScript to blunt XSS. And same site is your CSRF defense. Set those 3 by default. Treat any cookie without them as a bug. Which brings us to the protocol's most important upgrade, HTTPS. Same methods, same headers, same status codes. It's still HTTP, but wrapped in a TLS tunnel on port 403 instead of plain text on port 80. That wrapper buys you 3 things at once: confidentiality, so nobody on the network reads your traffic; integrity, so nobody silently injects ads or malware; and identity, so the certificate proves you're actually talking to the server you think you are. In 2026, plain HTTP is effectively deprecated. Browsers shame it, and roughly 95% of the web has moved on. So, how does that TLS tunnel actually get built? 4 steps, and with TLS 1.3, it's a single round trip. The client opens with a hello. Here are the cipher suites, TLS versions, and the server name I'm trying to reach. The server replies with its own hello plus an X.509 certificate signed by a trusted CA. Both sides then run a Diffie-Hellman exchange to derive the same symmetric session key without ever transmitting it. Send a finished message, and from that point on, every HTTP byte is encrypted. That certificate the server presents. Let's open it up. An XY509 cert is basically a signed identity document. Subject tells you which domain it's for. Issuer tells you who vouched for it. Validity caps its lifetime, and the public key is what the handshake actually used. But the real magic is the chain of trust. Your browser doesn't trust example.com directly. It trusts a root CA like ISRG root X1 baked into the OS. That root signed "Let's encrypt R3" and R3 signed your server's cert. Break any link in that chain and you get the red warning page users never click through. TLS gets you an encrypted pipe, but the browser still needs to know what's safe to do inside that pipe. And that's where security headers come in. 6 of them carry most of the weight. HSTS locks the browser into HTTPS so an attacker can't downgrade to plain HTTP, Content Security Policy whitelists, where scripts can load from, killing most XSS. X-frame options blocks your site from being iframed for clickjacking. X content type options stops. MIME sniffing, referrer policy, keeps your URLs from leaking to third parties. And permissions policy shuts off camera, mic, and geolocation unless you explicitly opt in. Ship all 6 on every production site. It's the cheapest defense in depth you'll ever deploy. Speaking of browser-side defenses, here's the one that trips up almost every front-end back-end integration: CORS. By default, the same origin policy blocks JavaScript on app.com from calling API.other.com. Different protocol, port, or even subdomain all count as a different origin. CORS is how the server opts in by sending back access, control, allow origin, and friends to tell the browser this cross-origin call is sanctioned. And one hard rule: never pair a wildcard origin with credentialed requests. Always name the origins explicitly. Now let's zoom out and look at how HTTP itself has evolved. The semantics, methods, headers, status codes have stayed remarkably stable since 1997, but the wire format and transport underneath have been rebuilt twice. HTTP 1.1 gave us plain text simplicity, but only one request at a time per connection. HTTP 2 went binary and multiplex streams over a single TCP connection, though it still suffered TCP head-of-line blocking. And HTTP 3 throws TCP out entirely, running over QUIC on UDP, which means faster handshakes, no HOL blocking, and seamless connection migration when your phone switches from Wi-Fi to cellular. With transport handled, let's talk about the cheapest performance win you'll ever ship: caching. Cache control is a tiny header with enormous leverage. Public versus private decides who can store the response. No store locks down sensitive data, and max age sets the TTL in seconds. The combo you'll reach for constantly is public. Max age 31536,000, immutable on hashed asset URLs, a full year of cache, 0 revalidation, because the file name itself changes when the content does. Get this right, and you've cut 80% of your bandwidth before touching a single line of application code. Now zoom out from the protocol itself to what we build on top of it. REST, GraphQL, and WebSockets all ride on HTTP, but they solve fundamentally different problems. REST gives you cacheable resources with standard verbs, perfect for public APIs and CRUD, at the cost of overfetching and chatty round trips. GraphQL collapses everything into one endpoint with a query language, so mobile clients fetch exactly what they need, but you trade away easy HTTP caching. WebSockets upgrade the connection to persistent and bidirectional, the right call for chat, trading, live notifications, anywhere latency matters more than cache friendliness. The senior move isn't picking a favorite, it's matching the style to the workload. Which brings us to the moment things break, because they will. 6 tools handle 90% of HTTP debugging. Start in browsers, dev tools for anything user-facing. Drop to curl or HTTP when you need a clean terminal request without browser noise. Postman shines for building and saving complex API collections. When the protocol itself is suspect, Wireshark captures the raw packets, and OpenSSL's client is your scalpel for TLS handshakes and certificate chains. Match the tool to the depth of the question. Of those tools, curl deserves special attention, and curl-v is where the protocol stops being abstract. One command gives you the entire conversation. The asterisk lines are curl narrating the connection, DNS resolved, TCP established, TLS handshake completed, cipher negotiated, certificate verified. The greater than lines are exactly what you sent. The less than lines are what came back. Once you can scan this output top to bottom, you can diagnose almost any HTTP failure without guessing where it broke. And that diagnostic instinct is exactly what these 6 tickets train. Every one of them is a real ticket you will see. Expired certs, throwing net. Error cert date. Invalid. Fora card 1 from a malformed authorization header. Cores blocking a fetch because the backend never sent access control allow origin. Slow loads. Stale deploys from aggressive cache control. And 502s when the upstream is unreachable. Notice the pattern. Certificate, headers, cache, upstream. 4 layers. And almost every HTTP incident lives in one of them. Once you can place a ticket on that map in seconds, troubleshooting stops being guesswork and becomes routine. And once troubleshooting becomes routine, you start absorbing the truths nobody writes down. 5 of them. Plain HTTP is effectively deprecated in 2026. Browsers warn, search engines downrank, and Let's Encrypt removed every excuse. Cache invalidation will bite you more than any other layer, so hash your file names and version your APIs. Status codes lie. Always check the body too. HTTP 3 over QUIC isn't optional for mobile because it survives network switches. And when someone says the API is down, it's almost always CORS or DNS. Check the console first. And that's the journey. From a single request line in 1991 to encrypted multiplex streams over QUIC. 5 pillars, foundations, methods and status codes, headers, HTTPS and security, and modern HTTP in production. When you want the source of truth, go to the RFCs, 9110 through 9114. Practice with curl, DevTools, and Lighthouse. And when you're ready, the TLS Deep Dive is next. Welcome to HTTP Fluency. Now go build great things and help good humans.